Welcome to This Evening with Heidi Cullen, part of our Science Talks lecture series at Elmhurst College. This lecture has been selected to be recorded for Chicago Amplified, a web-based audio program that captures some of the most exciting and informative cultural programming in the Chicago area. In your printed program, you'll find out how you can hear this lecture again or share it with others through Chicago Amplified. At this time, I'd like to ask that you please make sure your cell phones are turned off. And now it's my pleasure to introduce to you the president of Elmhurst College, Dr. S. Allen Ray. Thank you.
Good evening, everyone. Welcome. This is the Roland Quest Lecture, established here at Elmhurst College to bring new ideas and outstanding lecturers to our campus. It also contributes, of course, to the intellectual vitality of the campus and community. The Quest Lectures honors our alumnus Roland Quest, class of 1936, a former McDonnell Douglas engineer who performed design work on the original space shuttle. Quest was also a boat designer and the owner of Quest Marine Company. Started in 1996, the Quest Lectures quickly became an enormously popular series. Previous Quest lecturers include Robert Ballard, Paul Sereno, Sally Ride, Jean-Michel Cousteau, Brian Green, Mitch Albom, Anna Quindlen, Gail Collins, Elizabeth Berg, Angela Burt Murray, Sebastian Younger, Paul Anastas, Joshua Foer, and Dr. Siddhartha Mukherjee. To introduce this evening's speaker is Dr. Kimberly Lawler-Sagrin. Dr. Sagrin is the Associate Professor of Chemistry here in our Chemistry Department, and she received her doctorate in Theoretical Physical Chemistry from Cornell University. Following her doctoral training, Dr. Sagrin joined the faculty of Cal State University in Fresno, where she was awarded early tenure in 1999. She came to Elmhurst in 2002 after serving as Associate Director of the Searle Center for Teaching Excellence at Northwestern University. Her research interests lie at the interface of computational, physical, and inorganic chemistry, and her work has appeared in the Journal of the American Chemical Society, Inorganics Chemistry, and other publications. Dr. Sagrin's pedagogical interests include online education, the use of computational chemistry in the chemistry curriculum, and developing problem-solving skills through active learning. Dr. Sagrin.
Hello. It's my great privilege to introduce our speaker for this evening. Dr. Heidi Cullen is Vice President for External Communications and Chief Climatologist at Climate Central, a nonprofit research and journalism organization. In her dual role as research scientist and correspondent for Climate Central, Dr. Cullen reports for a diverse set of news outlets such as PBS NewsHour, The Weather Channel, and Salon.com. She is the author of the book, The Weather of the Future, Heat Waves, Extreme Storms, and Other Scenes from a Climate Change Planet, published by HarperCollins. Before joining Climate Central, Dr. Cullen was the climate program manager at the Weather Channel. She helped create the series Forecast Earth, a weekly series focusing on climate and the environment. And she was the Weather Channel's first on-air climate expert. Dr. Cullen earned her BS in engineering from Columbia University and her PhD in climatology and ocean atmosphere dynamics at the Lamont Doherty Earth Observatory of Columbia University. Her research interests include droughts, how large-scale mechanisms cause droughts, and how to use climate information to manage water resources. Dr. Cullen has worked as a research scientist at the National Center for Atmospheric Research and received the National Oceanic and Atmospheric Administration's Climate and Global Change Fellowship. She worked at Columbia University's International Research Institute on Climate and Society, applying long-range climate forecasts to optimize water resource management at the Itaipu Dam, the world's largest hydropower facility located on the border of Brazil and Paraguay. Dr. Cullen serves as associate editor of Weather, Climate, and Society, a journal of the American Meteorological Society, and is a member of the National Oceanic and Atmospheric Administration's Science Advisory Board. In 2008, she received the National Conservationist Award for Science from the National Wildlife Federation. Dr. Cullen is a visiting lecturer at Princeton University, where she teaches the course Climate Change Communication. In her words, she teaches this class in order to help students better understand the world they are inheriting and how they can communicate climate science with integrity and passion. We are fortunate to have her with us today to share with us her passion for climate science. Sorry. Please join me in welcoming Dr. Heidi Cullen, whose Quest lecture is entitled The Weather of the Future.
Thank you. Good evening, everyone. Can everyone hear me okay? In the back? Okay. First of all, thank you so much to everyone at Elmhurst. This has been a wonderful day, and I was noting over dinner that as an undergraduate, I minored in religion, and one of my heroes was Reinhold Niebuhr, and I just learned today, coming here, that he was a graduate of Elmhurst, so it's truly, truly special for me to be here. I'm going to speak for about 45 minutes, and you know, the title of my talk is basically seeing climate, seeing change, and we're going to talk a lot about how to see things and how to see climate, because it's one of those phenomena that's actually kind of tricky to see, and how to talk about climate is trickier even more. So, you know, I start with this image of an ice flow, essentially an iceberg, and when you ask most Americans what they think of when they think about climate change, most Americans think of melting ice, and I think part of what I'd like to cover tonight is just how climate change is actually much bigger than that. Really, you know, this talk will focus on climate science, but it's also a talk about journalism and communication, the communication of risk, about government and how we solve big problems, about innovation in our country. So it's meant to take this topic of climate, but actually look at ourselves and see how we tackle really big problems. So what are climate scientists so worried about? Basically, this is output from the NCAR climate model, and what it shows you, taking 1 year time steps out to the year 2100, is the planet warming up. NCAR's model is one of the best climate models out there, and basically climate scientists are worried about the fact that, you know, by the end of the century we could be somewhere between 3 and 11 degrees warmer. And that's a range, right? So there's uncertainty in that estimate. So we're worried about the fact that the planet is warming up. We can't tell you exactly how much it's warming, but there's decisions that need to be made based on this finding. You know, and you know, I like to sort of frame climate change as basically a very simple finding that was based on research that started well over 100 years ago, that found that our decision as a society to burn fossil fuels had some negative impacts. Those impacts play out over timescales that are difficult to see, which is why this is a tricky problem to address. But this issue is based on a scientific finding. And how we communicate that science and then how we act on it is one of the toughest challenges out there, I think. Communicating risk is inherent to the issue of climate change. And if you go back to our founding fathers, basically Thomas Jefferson himself said that wherever the people are well informed, they can be trusted with their own governments. This notion of how we communicate risk is one that ties back directly to the scientific community. And I said that the talk is about climate science, but it's also about the role of science in general in our society. And I actually think it's this microphone, maybe. That when you look back over U.S. history, there was a very important book written by Vannevar Bush, and it really kind of set the tone for the relationship between science and government, and it set the difference between applied science and pure research. And basically, this slide here is just meant to showcase the different kinds of science. You know, if you think about Niels Bohr and sort of the quintessential example of pure research, just research for knowledge's sake, and then we look at purely applied research. And if you think of Thomas Edison as someone who was basically trying to solve real problems, and Pasteur as sort of someone who was operating in between. Climate change is a societal problem that has long time scales, and we actually don't have enough information to solve the problem at this point. We haven't figured out all of the energy solutions yet. We haven't figured out all of the adaptive strategies yet. And so, whereas science, in many respects, caused the problem, science came to understand this problem, it's also going to be probably the most significant way that we solve it. And so, there's been a lot of talk about innovation in the United States. And this was actually, I don't know if anybody caught it, in the Sunday Times recently, just a very nice op-ed about the history of Bell Labs and the innovation at Bell Labs. And when you look back, all of the amazing things that came out of that laboratory, I mean, everything from solar panels to lasers, so many quintessential things that we take for granted today came out of this laboratory. And I show this more or less to say that climate change and this notion of how do we all come to fit on this planet sustainably is going to be intricately tied to how we approach the sciences. So just in terms of the things that I'd like to cover, as someone who was trained in the sciences and then moved to the media, essentially, I've always been really fascinated by how the public perceives different problems. So I want to talk a little bit about just public perception of climate change, and then let's just work through how do you see climate, how do we know that it's really us and that we're causing it, and then how do we actually fix the problem? So let's start with just a basic structural issue. Psychologists who've been studying climate change and sort of the larger philosophical issues of how do we grasp this problem and then how do we actually will ourselves to action on it. Very interesting look at the human brain. And if you think about the human brain as having two different halves, think of the amygdala and sort of what we would call the ancient part of the brain, that part of the brain that's very much fight or flight. Not really well equipped to think of climate change as something that is truly dangerous, right? Stampeding elephants, a gun to the head, those are the kinds of things that capture that part of our brain. But you can argue that the prefrontal cortex, that sort of rational, forward-looking, compassionate side of our brain, that's the part that actually makes us human. The ability to look out over time and make decisions that are based on uncertain information, that's the part of the brain that actually we need to connect with when we think about climate change, because it doesn't relate well to the decision making that goes on the amygdala side of the brain. And I don't know if anyone has been reading Daniel Kahneman's book, Thinking Fast and Slow. We're going to talk a little bit about how we make decisions and persuasion, and he touches upon the differences between how we approach problem solving, and climate change is very much linked to just how we perceive risk, essentially. So I guess as a scientist, I view public opinion polling as something that I treat with a certain amount of distrust, and I think the easiest way to bring it to you is not to present the latest poll or my favorite poll, but to just show you all of the polls and the spread. So the underlying question is, do you believe in global warming? Do you believe that the Earth has warmed? And the range is anywhere from 49% up to the high 70s. Interestingly enough, Gallup is on both sides of that extreme. And one of the things that you learn when you begin to study public opinion polling is that the way you ask the question is incredibly important. And it is a flawed science, but it is also very, very helpful and very interesting. But I think the main takeaway is to just say that there's a fairly wide spread in the polls with respect to what Americans think about climate change. Now, I think the important part is to look at it over time. I'm a classic climatologist. I want to see the data over long periods of time. I want to see all of it bundled together. So this is all of it over time. And what you should really take away from this is that public perception of the issue was actually fairly high in 2006, 2007, and it really dropped in 2008 and 2009. And from the social science standpoint, a lot of folks have been trying to understand what was it that happened that really changed people's opinion, made them less concerned about it. I'll say that the economy certainly played a pretty significant role. It's probably not a surprise that it tanked right when our economy took a nosedive. Some people also have linked it to the fact that our weather actually cooled off in 2008. We had an incredibly cold winter, and that our large-scale perception of climate change is influenced by overall weather patterns. So that's some of the ways that folks have begun to take this data apart. So in terms of seeing us, seeing Americans and how we approach the issue of climate change, I'm going to talk about the science of it as well, but just in terms of polling Americans, where do they stand on the issue, and where do we need to help and communicate more broadly on it. This is some research that's been done, it's an ongoing survey that's been done by some of my colleagues at Yale and at George Mason, and I think one of the easy ways to think about the U.S. when it comes to climate change is to think about 6 Americas. Those 6 Americas go from the alarmed and the concerned down to the doubtful and the dismissive. And for social psychologists and political scientists, you focus a lot on the folks who are at either extreme. Those are the folks that we call the issue public. Those are the folks who tend to call their legislators and say, do not vote for cap and trade, or vote for cap and trade. Those are the people who really tend to push issues forward. Again, these circles have changed in size over time. We've seen them go up and down. But relatively speaking, on either extreme, it's about 10-12%. Now, I think it's useful to actually aggregate it even more and actually think of it as 3 Americas. You've got the folks who were very passionately aware of the issue, and really all they want to know is how to fix it. They say, don't give me any more science, don't tell me how bad it's going to be, just tell me what do I need to do to solve this problem. Then, where most Americans stand at this point, they're kind of in the middle, they're a little bit on the fence, and they're saying, okay, I've heard of it. I agree that it's a problem. I don't know if I would rank it as my top 5 problems, but how is it going to affect me where I live? Why should I care about this issue? And then finally, the folks on the end, this sort of doubtful and dismissive category, they basically don't trust the science. They say, explain to me why I should trust you as a scientist and why I should trust the data, which I'm going to show you next. So, in television, we always learn that you need to know your audience, and that's, you need to know what questions they have and how to answer them, and under what circumstances you should address these things. And I think it's really useful to know your audience in this case as well, because different folks have different questions when it comes to climate change. Hopefully we'll address all of them. So I'm a climate scientist by training, but I've done a lot of work recently with psychologists on this issue, because like I said, I think there's something about this specific problem that makes it trickier and harder for us because of our wiring, essentially. And been doing some work with a colleague at Stanford and have been kind of reviewing the literature on persuasion and public perception. And Daniel Kahneman's book, Thinking Fast and Slow, is sort of a really nice, newly published survey of how we make decisions and public perception. This is one of the groundbreaking books that came out back in the 90s, The Rational Public, and it really begins to ask and answer questions about how do you make someone concerned about issue? How do you persuade someone to believe that what you're saying is in fact right? I mean, as scientists, we always feel that the facts will win. I mean, I will just tell you what's true, and you will care about it. But needless to say, we're bombarded by people wanting to persuade us to do things. I mean, just coming here from the airport, I was counting the number of billboards, and so people are constantly trying to persuade us to do things that they think that we should care about, whether it's buy Coke or Nike sneakers, or choose a healthy diet and lose weight and exercise more, right? So we're in an environment where we're constantly trying to be persuaded to do certain things, and for climate scientists, there's an issue that we feel is a truly important one. How do you express that and communicate that in a way that feels commensurate with the risk that we think the problem comes along with. And these are some of the classic steps that you need to go through to persuade someone. And I think, from a standard advertising campaign, it's really just exposure. Coke just wants you to see their ads so that when you approach the machine to buy a drink, you just have that slightly greater percentage of hitting the button. And if they permeate the landscape with advertisements for Coke, there's just a certain percentage of people that will be pushing that button in their direction, and it's a simpler campaign. But when it comes to sort of larger efforts like healthy living and education, it's actually really important for folks to understand, comprehend your message, retain it, and accept it. And so I think when it comes to education, we're dealing with a much trickier problem. So basically, one of the key findings of persuasion literature is that, or one of the basic tenets is that people don't change very much over time. This is again, think of it as a climatology of sorts of racial attitudes, and it spans over 30 years. And one of the basic tenets is that we don't change our minds very much over long periods of time. It takes a really long time to penetrate sort of popular attitude. And this is with respect to questions about race. And what's interesting is that incredible legislation was passed in the 60s, despite the fact that the majority of Americans still held certain attitudes and beliefs. And so, I speak about this issue public, this part of the public that really cares about issues. There's tremendous potential for enormous change. And even though, as a society, we tend to move and change our ideas fairly slowly over time. And if you read Kahneman's book, which I highly recommend, he shows sort of all of the ways in which our thinking processes can be flawed. So for example, selective affiliation. We tend to associate with folks who hold our own beliefs. It's a very common way of affecting our perception of things. Another is selective memory. We tend to remember things that support our point of view, which starts to, when you read his book, you start to, question your decision-making processes. It's a very healthy thing. And selective perception is that, you tend to think that more people agree with the way you think. So if you do a poll and say, how many, do you believe in global warming? And, how many people do you think share your belief? If you say, I believe in global warming, there's a pretty good tendency that you'll say about 60% of people share my belief. Whereas if you ask that question to someone who doesn't believe in the science of global warming, they'll also say that they think about 60% of the population shares their belief. So there's a selective perception that more people share your belief. So I just set this up as kind of a backdrop of how we communicate big issues that have massive implications for our government, for how we do science, as kind of the backdrop of how these things play out. So it's been interesting to see, with respect to climate change itself, what drives concern. And recent studies basically show that belief that climate change, and belief in this case is used in a social science frame, like belief is a standard social science term, but it's acceptance of the science of climate change, if you will. You've got to accept that it's caused by human activity. Concern is directly linked to whether you feel that climate change, you accept that climate change is caused by human activity. That's a very specific driver for concern. Also is trust in what scientists say, belief that scientists agree, and then the level of attention it's being paid to, specifically media coverage. So let's look at trust. Trust is one of these things that is so critically important. And for those of you who follow kind of the inside baseball aspects of climate change, there's constant attacks being made on, can we trust these scientists, or why are they doing this? This is a recent poll that just looks at, who do you trust to tell you about climate change? Climate scientists remain sort of the number one trusted source, but other sources include TV meteorologists, your local doctor. So we go to specific places to get our information. So, okay. So we trust scientists, by and large, we look to them to give us information about climate change. So before I go into my attempt to describe the science, there was a recent piece in The Onion, which is, as I'm sure you guys know, it's a satirical news show, and I thought did a very nice job of showing perhaps some of the limitations of scientists as communicators. Take a look.
This is the Onion News Network. Report first, ask questions later.
Now, let's look into a somewhat perplexing story from the world of science. People are reporting that climatologists around the country have been behaving very strangely recently. Let's go to Andrea Bennett in Cambridge, Massachusetts for more. Hello, Andrea. What's going on?
Well, Brooke, we just don't know. Something definitely seems to have spooked the climatologists here. They've been pacing around, gesticulating wildly and making a lot of strange noises.
Well, I hate to see them all agitated, but these little professors sure do look funny, flailing their skinny little weak arms and pushing their glasses back up.
Yes, I suppose.
And what is that chattering sound that they're making, Andrea? Can we listen to a little more of that?
Well, it's similar to their normal vocalizations, but about a third faster and twice as loud.
When sea level does cross a threshold, it's very difficult to reverse that rise. So
Again, we're not sure why, but it's definitely not the first time we've witnessed this sort of behavior among various different types of scientists.
Now, Andrea, don't some people believe that scientists can actually sense danger coming? I mean, do you think that that might have something to do with the way that they're acting?
Well, there are those who believe that or think scientists can tell when someone has cancer or is going to die, but of course other people think that's pretty silly.
Now, as far as climatologists there in Cambridge, I understand that they've actually been approaching humans. Is that right?
That is. Now, they're usually very timid, but one came right up to me today. I am not lying. He was this close and handed me this.
Amazing. Well, maybe someday we'll know what all this jumping around is all about. Thanks
Yes.
so much, Andrea.
You bet.
I have to laugh every time I watch that. And I have to say, I know all of the climate scientists that they featured in that piece, and they're wonderful people, and their message is really important. And the question is, you know, how do we communicate it right and with integrity, and so that we can continue to make sure that we have the trust of the public. So, you know, I mentioned that one of the other things that drives concern is whether Americans believe that there's a consensus, whether they think climate scientists agree. Now, this is sort of where we begin to see things fall apart. A lot of folks still think that there's tremendous disagreement among scientists. I'll say that, you know, within the mainstream climate science community, it's you know, a well-established fact, and we'll walk through the body of evidence. But to the American public, there's still a lot of debate. This is still a hotly debated issue, if you will. And then I mentioned that concern is tied to media coverage. So basically, Bob Bruhl, a professor at Drexel, has been covering media coverage going back into the 80s. And as I was showing you before, public opinion of climate change was really at a peak in 2006, 2007. You can really see that here. It's reflected in news coverage as well. And then after that, it tanks. And I'll say that 2011 was the lowest media coverage going back to 2003. So the story really fell off the map. And, you know, a lot of work has been done trying to just understand, you know, what was going on. But, you know, needless to say, the country had serious problems over that period of time. And science journalism itself, you know, was just very, very dramatically impacted by the downturn in the economy. But there was a lot of other stories to tell as well. So, you know, it sort of tease up this notion of the media landscape. I mean, the media landscape is changing dramatically. A big FCC report came out this summer. One of the big takeaways is that, you know, basically newsrooms have shrunk. We're now down to pre-Watergate levels. So, you know, there was a phrase that was coined in that FCC report, which was hamsterization. You know, fewer journalists asked to do more things. And that's really affected media coverage. And it's certainly affected science coverage, which sort of demands a certain rigor and a certain amount of time and dedication, and not really having the bandwidth to tell sort of trickier stories that play out over longer periods of time and have kind of intricate outcomes and policy decisions. So I want to now just kind of shift into the science part. And basically, when it comes to sort of the sociology of communicating climate change, there's 4 key facts that you need to walk through for the majority of Americans to get them to the point where they feel like this is an issue that warrants concern. First, you've got to convince them that it's real. You've got to convince them that it's a threat. You've got to convince them that it's us, kind of getting back to the it's our fault part. And then finally, and as scientists, I don't necessarily think we've done a good job with this, You've got to talk about how we can fix it. If you don't offer Americans, and this is where sort of the history of innovation and entrepreneurship in our country, I think, really plays into how we embrace problems. If you don't give us a way to fix a problem, don't tell us about it, right? And that really plays into the climate change story as well. So talking about solutions is really important. All right, so let's talk about climate, okay? When I was at the Weather Channel, I was constantly being asked about, what's the difference between weather and climate? What is climate? And I finally kind of came up with at least the way I sort of see it in my head. And you need a Jackson Pollock painting to show how I see climate in my head. And, and what I will say is that it's not a mess. It's chaotic. It's complicated, right? And what's interesting about a Pollock painting, and the reason why I choose a Pollock painting to try to illustrate what climate is because Pollock had this very interesting way of painting, right? He would put the print on the floor, and he would then basically take his selected color, and then he would step down the canvas. And for the engineers in the audience, if you do like a Fourier transform, or if you do a mathematical analysis that pulls out all of the different frequencies of that painting and its colors, you'll get the different sizes of his steps. And so if you think of climate like this complex piece of art where you have all of these different systems playing, or think of it, if you will, like an orchestra where you have all of these different instruments and they're playing at different time scales, right? So if you pull apart all of the different colors in a Pollock painting and you look at their frequencies, that's kind of what climate is. You've got ice sheets that grow and shrink over long periods of time. You've got things like El Nino, which fluctuate on 7 to 10 year time scales. You've got the seasonal cycle. So you've got all of these different things going on at different time scales, and they all add up to produce, what we see. And if you think of weather as just, the daily aspect of it, climate is just this large thing, this large orchestra playing over incredibly long time periods. And then when you think about climate change, you think about this steady drumbeat of warming going on in the background. That's us. So we then become part of that orchestra. So I started out as actually a paleoclimatologist. I was very interested in a period called the Holocene, which is the last 10,000 years. And what makes the Holocene kind of intellectually interesting is the fact that if you look at this graphic, the flat part is the Holocene. The Holocene was a relatively stable climate. I mean, there was fluctuations on sort of decade-long timescales, but for the most part, the envelope of variability was pretty small. And interestingly enough, complex human civilizations came about at roughly the same time, which begs the question, to what extent does complex human civilization demand a fairly stable climate? And so tons of research has been done looking at ancient civilizations and the connection between climate change. I did some work in Syria looking at the Akkadian civilization, which was the world's first civilization, and looking at the causes of its collapse. And if anyone has ever read Jared Diamond's wonderful book, Collapse, he looks at how these somewhat invisible things play out in the background and can eventually have just massive effects. I mean, if you think of Easter Island as sort of the classic example of, what was the person who cut down the last tree on Easter Island thinking as he cut down that tree? These are sort of the kinds of questions that come into play when you think about climate. So, like I said, there's numerous examples through time. Some new research on the Mayan civilization has just been published as well, looking at the role of climate in the collapse. And I guess what I mean to say is not that climate change caused these collapses, but it played an important role. It sometimes, was that straw. And you look through archaeological history and human history and you see tremendous things, plague, warfare, you name it, but climate is also one of those players, and it can grow and shrink in its importance over time. So how do we kind of then work our way into this tremendous variability over natural variability over these different timescales? So let me say that as clearly as I can. There's a lot of natural variability. Yes, the climate has always changed. What is it? Why do we think that we are suddenly so important? part of the answer is the timing with which this change is happening. And then, secondly is just to say that we know that natural climate variability has tremendous implications. So if you push that, it's to suggest that it's going to have even bigger ramifications when we add ourselves to the mix. So I love to show this picture just because it has tremendous historical significance. This is Svante Arrhenius, who was the first essentially to ask the question, what happens to our temperature if we mess with carbon dioxide? If you think of carbon dioxide, this heat-trapping greenhouse gas, as a thermostat, a way to turn up the thermostat or turn down the thermostat, he was very interested actually in ice ages. And so he was starting to ask the question, okay, if we cut down carbon dioxide in the atmosphere, how much would the planet cool? And interestingly enough, he was sitting there in the 1890s, sort of looking at the birth of this industrial revolution and looking at the burning of fossil fuels around him, and then said, well, gosh, if we're burning these fossil fuels, we're actually putting carbon dioxide into the atmosphere. So, how much would the atmosphere warm if we, doubled CO2? He did the very first back of the envelope calculation for doubling of CO2. And interestingly enough, he came up with an answer not so different from our climate models, about 8 degrees. But where Arrhenius's thinking then began to absorb some flaws was the time scale, because he said, I don't think climate change is such a big deal, because if I factor in the growth rate of consumption of fossil fuels based on a linear population growth, that was his mistake. It's like it'll take at least 3,000 years for carbon dioxide to double. Needless to say, population has grown a little bit faster than that. And Arrhenius also thought, it sounds like it could be kind of nice. Then, this is why science is a progressive process over time that has lots of debate in between. Then you have Bert Bolin, who's actually the father of the Intergovernmental Panel on Climate Change. Bert came along and said, well, let's kind of think about this a little bit more. I suspect that given actual population growth rates, consumption of fossil fuels, we'll see roughly a 25% increase in carbon dioxide by the year 2000. So he was doing this calculation, back in the 60s, 70s, 80s. At the same time, that was his forecast. At the same time, amazing gentleman by the name of Dave Keeling at Scripps said, you know what? Enough theorizing. I'm gonna measure this. I'm gonna build an instrument that can measure carbon dioxide in the atmosphere. We're gonna watch it grow. I'm gonna make a prediction, but now we're gonna measure it and see what actually happens. Keeling constructed a mass spectrometer, sort of a breathalyzer, if you will, for the atmosphere. He stuck it in the middle of the Pacific Ocean in Hawaii, a place where he felt was pristine, wouldn't be contaminated by the traffic of San Diego or LA, and he began to take carbon dioxide measurements. And this is what he found. It's going up. Now, he took it a step further in the sense that he was able to chemically fingerprint that carbon dioxide. See, carbon dioxide comes in 3 different flavors based on the isotopes, C12, C13, C14. And if you think of fossil fuels, ancient, the radiocarbon aspects have decayed. So there's essentially no C14 and C13 in a molecule that's been combusted from fossil fuels, so we can fingerprint it. It's different from the CO2 that we or the plants will breathe out. And so what Keeling was able to do was to basically estimate that about 1 out of every 4 carbon dioxide molecules in our atmosphere today was put there by us. This was just one technique for actually fingerprinting or attributing the CO2 to us. There's other ways to do that. And this steps us a little bit into modeling. And I talk about 2 aspects of the science called detection and attribution, because these are really at the heart of why scientists feel very strongly that it's us, that we know it's us, and it's real. So, I'll say that I studied engineering and I worked on Wall Street for a little while, and to this day I can't really look at a climate variable like temperature without kind of thinking of the stock market. It's very similar kinds of techniques, trying to figure out trends versus cycles, and detection is very much trying to understand whether we're seeing a cycle or a trend, right? And you can basically statistically test that and be able to say that that is indeed a trend, and you can do that using computer models run over incredibly long time periods to just say, does Mother Nature on her own randomly generate a trend like the one we've seen over the past 100 years? And the short answer is, Mother Nature on her own doesn't generate trends. She generates lots of natural cycles that will peter out over time, but she doesn't generate trends. I'll come back to you at the end, okay?
What did your chart show?
This is, sorry.
How far out is that?
Sorry, this is observed temperature data that goes back to the 1800s.
The end of the chart, is that present? Or
Yes, I'm sorry. I'm like leaning over to see my own graphic, but yes, this is the observed temperature trend, okay?
That's the end of the chart.
So this is the beginning, and this is where we are today, roughly, okay? So what we're basically asking the question is that trend real, or is it just a cycle, okay? The other aspect of detection is attribution, is saying, yes, it is a trend, and then attributing it to us or to some other phenomenon. And the statistics and the methodology that attribution science is built on is epidemiology. It's very similar to looking at, a cause of death. So doing an autopsy and saying, okay, to what extent did cigarette smoking cause lung cancer, or poor eating habits lead to heart disease? Similar kinds of statistical techniques are used. And another way to look at it is baseball, right? If you have someone who had a great season and was accused of taking steroids, the only way to really be able to attribute that to steroids is not to look at one specific baseball game. It's to look at the entire season and compare it to previous seasons, right? And that's a way to kind of think about how attribution is actually working. So we take a climate model and think of a climate model as kind of a twin Earth. What's so tricky about this problem is that it's so big and we don't have another Earth to practice this stuff on. So a climate model serves as our twin Earth. We just happen to break it up into tiny little pieces and then use all of the equations of state in each little grid box to then recreate how our planet creates its temperature over time. And then we start to tweak it, essentially, and we add different things to it. This is actually the climate model. It's basically just a series of massive computers. These are some of the most complex computational exercises done. And this is the one at the Geophysical Fluid Dynamics Laboratory at Princeton. And we then just begin to ask ourselves basic questions. This is the latest high-resolution ocean circulation model that GFDL has, and this is just a way to show you that over time our model resolution has gotten better. So it used to be that one grid square was about 200 kilometers. Now it's about 25. So we can resolve a lot of differences now in these models. Now keep in mind, when it comes to things like tornadoes and hurricanes, even though this model is 25 kilometers, just think about how tiny a hurricane, a hurricane even, and especially a tornado is within that grid square. So those things are difficult, very difficult to resolve, but we can get at the bigger stuff. So climate forcings are basically all of these different things that we've kind of gone through, things like El Nino, volcanic eruptions, the solar cycle, and then us. And what we can do in our climate models is put all of these parameters in and then see what our climate model does in terms of reproducing the observed temperature. We know what the real Earth has done in terms of global average temperature over the past 100 years. Let's see what our climate model does with these different flavors of forcing. So again, here's the observed temperature record. And I've highlighted this in blue just to kind of show you that what we're really trying to recreate in our climate model is this upward, this downward, and then this trend back up, right? Because I said climate's a little bit complex in the sense that even if you have a trend, there can be shifts on shorter time scales within that trend, and we need to be able to reproduce all of that to feel that our climate model is correct. So let's say model number one, this is only Mother Nature, right? We spin up our model, we run it out over time, we're trying to reproduce the black line. This is a climate model with only Mother Nature. There's no trend in it. Mother Nature on her own cannot create that uptick that we really see, say, starting in the 1970s. Okay, model run number two. This time, only carbon dioxide, greenhouse gases from human activity. This time, we can't create that little cooling spell that we saw from the 40s to the 60s. We get the trend pretty nicely, but we don't get it. So it's not just us, and it's not just Mother Nature. When we try to recreate all of the forcings that we know are in play, this is what we get. The red line is the model, the black line is observation. So the only way to get incredibly close to the observed temperatures that we've seen is to put everything into the model, to put solar activity, volcanic forcing, ocean dynamics, and human activity. So that's how we say with certainty that humans are responsible for a large degree of the warming that we've witnessed, okay? So, like I said, when I was at the Weather Channel, I was always getting questions about the difference between climate and weather, and you know, leave it to a great author to say it best. Climate is what you expect, weather is what you get, right? So that leads to the question of, okay, how does climate work its way into the weather, okay? It's actually not that complicated. If you warm up the average temperature of the planet, okay, if you basically, this is the mean, and you shift it up, our weather is going to be influenced in fairly specific ways. We can expect to see more heat extremes, and we can expect to see more rainfall extremes. Warm the planet, more moisture in the atmosphere, more fuel for storms. So one of the major findings of climate science, climate change science, is that climate change piles up in the extremes, and so we should expect to see more extreme weather. Here's what we've observed over the past 100 years, right? This is out to 1895. So this is in the United States. Since 1895, we've seen overall warming. Now, like I said, it's a little bit complicated. Southeast has actually cooled, right? So not uniform warming by any stretch. Certain parts of the country, certain parts of the globe are warming more than others. Think of it as rainfall. Interestingly enough, over the past 100 years, the East has gotten wetter and the West has gotten drier. This is very consistent with what we see in climate models. And within that, interestingly enough, we've seen a shift in the way the rain falls. What this basically shows is a shift towards more heavy precipitation. So when it rains harder over shorter periods of time. The strongest signal, 67% increase in the Northeast. You know, 2011, we all know it has been an incredibly extreme year in terms of weather. 14, at least, billion-dollar weather disasters, according to NOAA. Talk to a reinsurance agent, and he will basically say this is what we see as the new normal. As a reinsurer or an insurer, I'm looking at how extreme weather is going to impact my policies. Munich Re recently released this. This is the fresh data going up to 2011. This is global weather catastrophes, and you know, this increasing trend. Again, I'm not saying this is strictly climate change. It's also just more people. This is population growth. More people in harm's way. More people in places that have a lot to lose. The coasts, for example. I think the estimate that Wharton uses is that in terms of the insured losses, the capacity for insured losses along the Northeast coast, just the Northeast coast, is $11 trillion in potential. So we've got a lot of stuff in harm's way that's at risk. You know, and that's why I say that so much of this is about how we communicate risk and then how we make decisions around risk. So in terms of making the connection between climate change and extreme weather, I just want to leave you with this way that I found was really useful in helping me to see what climate change meant. Okay, so I mentioned attribution science. And so after the European heat wave in 2003, which if you remember back, you know, upwards of 50,000 people died, weeks of severely above average temperatures. It hit 104 degrees in Paris, very unusual. Statistically, it was considered about a 1 in 500 year event. So scientists took a climate model and reproduced the European heat wave, and then they asked the question, to what extent did climate change increase the risk, increase the chances of that heat wave happening, okay? Because this is really all about statistics, and that's why, you know, it's a tricky one to think of, you know, in sort of the amygdala part of your brain, because it's really just a piling up of probabilities. And so what they found was that human influence at least doubled the chance of summers as hot as the one in Europe in 2003. Okay, so it pushed the odds of that heat wave from happening. Is that scary? Not necessarily. It's interesting. But then when you run that model out in time, so what they did was they reproduced 2003, and then they continued greenhouse gas emissions, business as usual, over time, to see how the odds would change as you move forward in time. By 2040, the 2003 type summer basically starts happening every other year. And by 2070, the European summer of 2003 becomes the average summer, right? And I think that's when you kind of begin to get what climate change means and why, when I showed you that globe at the beginning that ran out through the end of the century, scientists say, I'm not sure that fits into the envelope of variability that we can successfully live within. That's kind of what is the scary part about this. And the really tricky thing about climate change that's still when I try to wrap my head around it, it's fascinating, right? But the thing about climate change is that by the time you really see it, it's too late to fix. I mean, talk about a really difficult societal challenge, right? Like, we are very visually based. And here's a problem where when you see it, it's too late to fix because of the time lags in our climate. Right now, our ocean absorbs about half of the CO2 that we throw up there, right? So we have all of these buffers within our climate system that are kind of picking up the slack for what we do. And by the time we really see it, Jeff Masters, who blogs for Weather Underground, if any of you guys follow him, he said it very nicely recently, which is, right now what we're seeing is what we did in the 1980s, right? That's weird. How do you deal with that? How do you prepare for something like that? So Miles Allen, a colleague at Oxford, rewrites the Mark Twain quote as this: weather is what, sorry, I can't even see it. That's right. Climate is what you affect, and weather is what gets you, right? So it's a different way to kind of look at this. And I feel like weather has been, as someone who loves the weather has always been this thing that was pure, right? It was something that we weren't part of, and that made it special somehow. And I think part of this is to sort of acknowledge that we're affecting it. We're part of that too. Our fingerprint is pretty much everywhere at this point. So, okay, solutions. Okay, I think it's useful because sometimes television writers say things better than scientists can, and I saw this on The Simpsons, and I just thought, yeah, who can say it better, right? So,
math done. Pine cone collected, permission slip signed. Now time for a break. A little social studies. What will Springfield be like in 50 years? Let's see what the computer says. That's horrible. What else? Oh my God. It just gets worse and worse.
And now, Ralph Wiggum will read his essay on Springfield in 50 years.
In 50 years, the vacuum cleaner will be quiet and not scary.
Next we have Lisa Simpson.
Oh, Ralph, how I envy your optimism. There is no Springfield 50 years in the future. With global warming trapping the CO2 inside our poisonous atmosphere, our superheated oceans will rise, drowning our lowlands, leaving what's left of humanity baking in deserts that once fed the world. And in the new Nineveh, darkness falls.
Lisa, your outburst was either a sign of deep emotional imbalance or a passionate response to a sobering truth. Luckily, the treatment for both is intensive therapy.
What's therapy gonna do for me when the world is in ashes?
Oh, I don't know. But when you go, could you return this Sports Illustrated for me? Someone must have put it in my bag. They do that, you know. They're always putting things in my bag.
Well, off to school where they'll prepare our little minds for a future we'll never see.
Sounds like someone's got a case of the Mondays.
I'm going to Disneyland.
I see trees of green, red roses too. I see them bloom for me and you, and I think to myself, what a wonderful world.
Bart, in my concurrent adventure, I learned a really important lesson. You can't wallow in despair. Face things as they really are.
So the point is not to wallow in despair, because sometimes, like I said, as scientists, we get to that part of my talk and we end it, and we're just like, okay, we'll see you later. So there's more to this story, and it goes back to the beginning, which is innovation and science and exploration and understanding and answering big questions. And honestly, that intersects with policy, and I once heard someone say that science is always political, but it should never be partisan. And I think that that's sort of the way I approach this as well. So when I get to this part, I think more about solutions and policy options, and how we can approach it. And the way scientists, as highly rational supporters of breaking things into little boxes and moving forward, we basically say you can mitigate, you can just cut emissions, or you can adapt. The fact that even if we went cold turkey and stopped emitting right now, there'd still be warming in the pipeline because of the memory in the system. We're going to need to adapt. We're going to need to deal with all the stuff that's in the pipeline. So, as an example of adaptation, I just think there's so many ways to look at this, which is to say that we are already affected by extreme weather and we don't have the infrastructure to deal with it appropriately. I was at the Weather Channel during Katrina, and I'll just never forget feeling incredibly useless as the climate scientist who thinks over these really long timescales of how to possibly help the situation that was going on. And I remember going back through the literature and just seeing that literally 20 years and 30 years earlier, scientists and engineers had gotten together to say, needless to say, New Orleans is incredibly vulnerable. We cannot tell you when a major hurricane will hit New Orleans, but we can tell you that it will at some point, right? This is the low probability, high impact kind of scenarios that we're not that great with dealing with always, right? And there it was in 2005, it happened. And New Orleans wasn't prepared, and one could argue still is not very well prepared. So the question is, how do you prepare for worst case scenarios? This is an example using earthquakes, which has nothing to do with climate change, but only to say that infrastructure is infrastructure. It protects you from all of the stuff that gets thrown our way. This is the February 2010 earthquake in Chile, 8.8, massive earthquake, and the death toll was high, but not nearly as high as in Haiti, which was a much smaller earthquake. And the difference is housing infrastructure. In Chile, because of their history of earthquakes, back in the 70s, they put into place rules that said that if you build a building, you are responsible for the damages. And so earthquake infrastructure is good. It's they've done a fairly good job of preparing for these situations. Needless to say, the infrastructure in Haiti was in very poor shape. And so you can just see that long-range decisions have a huge outcome. And I've been looking at some stuff just with respect to Hurricane Irene and the kinds of damages that Hurricane Irene did in places that we don't generally think of as places that get hit by hurricanes, like Vermont, right? When you look at flood insurance, you can see that those decisions are actually decisions that we aren't making very well either. The average person in the US will drop a flood insurance policy after 3 years if they don't have a flood. So there's, again, when I was talking about how we make decisions, selective affiliation, selective memory, those kinds of decisions also apply to, whether or not to buy an insurance policy. And so good policy will help us make smart decisions. So one of the thoughts is long-range flood insurance. When you buy a house, the insurance comes with the house. You don't have to make that decision each year to renew your policy. Building these kinds of long-range things into the decisions that we make, kind of like a mortgage, rolling things into mortgages, whether it's solar panels, wind turbines, or flood insurance. So on the mitigation side, I'm going to just very quickly reinforce the point that when I talk about climate, obviously I'm talking about energy, and that's why climate is such a tricky issue, is because it's fundamentally tied to our energy choices. And, I think it's just really important, again, to think long term. Right now, let's just say we use about 15 trillion watts, 15 terawatts of energy. By 2050, we're probably going to need about 30 trillion watts, right? So innovation, science research, how are we going to get all the energy that we need? We just hit 7 billion people. We know that these things are in the pipeline. How do we prepare for them? Short answer is there is no silver bullet, and I think that we all wish there was, but there's not. And so we've broken this problem into lots of little pieces, and problems with solutions that are in lots of little pieces aren't necessarily very sexy. They're kind of hard and tenacious and easy to forget about, but basically when it comes to solving the energy problem, it's kind of crossing all of these different areas. Energy efficiency, I just like to start by saying the low-hanging fruit. There's so much that we could do just in terms of energy savings. And the other really is increasing our portfolio. And there's lots of things we can talk about with respect to our energy portfolio. Lots of things on the table right now that are big issues. But I've got some numbers up here to just kind of give you a chance to think about this 30 trillion watts. Solar, basically what the sun gives us, about 600 trillion watts. So there's lots of potential to utilize solar. This blue box there, think of it 100 miles by 100 miles by 100 miles by 100 miles. That box is basically, if you filled that up with solar, that would give us all the energy that we would need in a year. And the solar folks will always say that, look, we're not saying we should do that. We're just saying that we should utilize enough space on our rooftops, gas stations, parking lots, just put stuff out there that adds up to that amount and basically diversify our energy portfolio by taking advantage of things. Same thing, with wind, tremendous capacity. Biofuels, we're going to need liquid fuels in some form. It's a given. We're going to need liquid fuels for transportation. So I think, the short answer is just diversification of the energy portfolio and admitting that if we're going to get to 30 trillion watts for the entire world, we're going to need to shift towards renewables. It's just a given. So, in conclusion, I'm sorry I ran over, is a great quote by Sherry Rowland, who actually got a Nobel Prize in Chemistry for his discovery of the ozone hole. But Sherry, being a very forward-thinking man, says it very nicely, which is, what's the use of having developed a science well enough to make predictions if, in the end, all we do is stand around and wait for them to come true? So that's the question. So with that, I will wrap it up. And questions now, or yes, questions now. Okay, we've got folks with microphones, and they're going to come around.
And if you would come to either side of the outer aisles, and you come to the mics, that would work well.
Are you ready? Okay. I'm sure you know that there are folks out there for whom facts mean nothing. Sometimes especially politicians. And so you know that there are folks out there, this is all a hoax, it's all being perpetrated by you-know-whom. What do you say to them? What do you say to them?
So this is the million-dollar question, right? Paper was just published looking at climate change opinion over time and what was the leading drivers of concern about the issue. And elite cues from our political leaders play a really large role. So when our leaders, our elected officials, don't show concern for the issue, it sends a large-scale signal that this isn't important. And my answer to that is, to acknowledge the fact that as an issue public, for the folks who really are concerned about the issue, elected officials right now are saying, my constituency does not care about this issue, and therefore I don't need to care about it either. And my sense is that the issue public who is not concerned about climate change is far more vocal. And that actually makes a really big difference in our political process. And I'll frankly say that obviously, lobbying plays a huge role as well. And let's just say that the team that has more money sometimes wins. I think that's been a discussion that's come up a lot. But to maybe just answer your question simply is, we need our elected officials to care, because if they don't, nothing will ever happen. And part of that can tie back to how we engage them and tell them that this actually does matter to us, because right now they don't think it does. But it's not a great answer,
Under international law, there's something called the precautionary principle, which prohibits activities that cause irreversible harm to the humans and environment. Since we have truth, facts, and reality on our side, don't you think our last chance is to have a very public trial on climate science, and then, once we have a conclusive legal verdict, we can finally get legislation passed limiting greenhouse gases?
I am a strong believer in the precautionary principle, and if that works, I would love it. I guess as a scientist, I think we do live in a world where, where facts don't necessarily drive all the change that we would like it to. I was reading somewhere recently where they said, facts add, but stories multiply. And, I didn't hit on the journalism side so much, but the kinds of stories that we tell around this issue and the ways that we can frame it for people so that they do feel more emotionally engaged. Here I am answering your question by saying, actually, we need to step away from the science a little bit. I'm a firm believer in presenting the facts, but right now, climate change, if you think back to the kind of amygdala part of our brain, we don't have an emotional connection to this issue. It doesn't feel dangerous and scary. When you poll people, Americans will say that climate change happens to other people in faraway places on timescales that don't matter. And I think part of the challenge is to make that understanding feel closer to the heart.
My premise is that there is a fossil fuel lobby that has sabotaged legislation in the past.
That's right. Yeah, there's a great book by Naomi Oreskes. I'm sure you've read it that outlines it very nicely, and I'm fairly comfortable saying that that's an important part of this. For everything that we can do, there's other folks that are going to hit hard back. That it ain't easy when you have a scientific finding that sort of suggests that we made a pretty big mistake in an energy infrastructure choice and that it needs to be rectified. That's a pretty big scientific finding.
Dr. Heidi, wonderful lecture. The Midwest and Chicago in particular is a very diverse area, most of which with respect to weather. And I don't think anybody lives in Chicago because of the weather. I can't think of a more diverse place. You talked about, was it 2003 with the horrible heat in Europe?
Yep.
We had that here in 1995, a high number of deaths.
Yeah.
And we were doing things out in the yard. Anyway, I'll try to be brief. And last year, about our blizzard here. Incredible blizzard, our second biggest blizzard. Very, very interesting test of our infrastructure here. And now this year, I predicted this winter that we're not going to have much snow because I bought cross-country ski. Thank you for laughing at my joke. It's true. And I read why they have this extremely horrible winter in Europe and why it's like this here. I read why that is the scientific reason. But I'm wondering just about do you have any general commentary about these wide fluctuations we have, and particularly with respect to here in the Midwest? Just just your opinion in general about this huge diversity we have, and it's changing faster and faster, and that's why I came here tonight, really wondering about what any comments you have about our part of the country specifically.
Yeah, and in terms of the long-term forecast, are you thinking as well, or?
Absolutely.
Yeah, yeah. I mean, this winter has been absolutely fascinating. I mean, I follow all of this stuff as well, and Europe basically. I think the important takeaway is that tremendous natural climate variability on these shorter timescales. This winter, the jet stream basically just never dipped far enough south in the U.S. In the middle part of the country, it has just been zooming along in Canada, but it has taken like a nosedive over Europe. Part of that is related to, as I'm sure you know, this phenomenon called the Arctic Oscillation. And people are beginning to wonder, again, it kind of gets to all of these feedbacks. So, to what extent is our fingerprint in some of this? I showed you sort of the long-term observations of how we've shifted to more extremes, right? So that's kind of like the really big numbers of, more heat overall. Midwest expected to get warmer, definitely expect to see an increase in the number of heat waves and of longer duration. We definitely expect to see that. And then, the rainfall does in the Midwestern part, strongest in the Northeast, but in the Midwest as well. We're going to see more of these heavy rainfall events. But doesn't mean that winter's going to go away at all. It also means that I'll just geek out for just 1 second. One of the interesting areas of research is to ask this question: to what extent does warming in the Arctic, does the fact that the Arctic ice sheet is melting, how does that play a role in our weather? I mean, it's playing a role somehow. How do we quantify it? How do we get the dynamics right? One of the thoughts right now is, you're melting ice, exposing more ocean, which means you're evaporating more water. And the thinking is that basically presents more fuel. And it's also, as the Arctic warms, this way of thinking about it is like the refrigerator door has been left open. So the Arctic is warming up, the refrigerator is warming up, but that cold air is like spilling out. And so it's going to be really interesting to see how that feeds back. But I think it's one of these issues where the extremes that we're seeing statistically, we expect to see them more often. And the predictability of the system is being influenced by the stuff that we're putting out there.
It's going to be more unpredictable.
That's, for the insurance business, that becomes a really interesting question. And trying to, characterize what these changes mean. And a lot of effort now is sort of going into, how do we characterize that increase in variability? What does that look like? How often are we going to break records and how? And so that's kind of like an active area of research, I would say. It's a great question, and folks are just trying to figure out. A paper just came out recently about tornadoes, trying to understand the climatology of tornadoes and how warming the atmosphere could influence that. And it's super tough. Yeah. Yep. Thanks for coming out.
You stated earlier in your lecture that one of the ways that you can tell that CO2 in the atmosphere is caused by us is because coal and natural gas and so forth don't have the C14 and C13 anymore. It's decayed away because they've been underground for a long, long time. What other ways do we have of measuring human activity for CO2?
Yeah, so the other way, there's several, but the major other way is when I was showing the climate models and how we can play with the different forcings in the model, we basically run simulations and try to get our model to reproduce the observed temperature record. So actual chemical fingerprinting is one technique, and then computer climate model simulations is another. And those are both reinforcing. They both show that the only way to recreate that trend is through carbon dioxide being basically burned via fossil fuels.
I got a small problem with that, in that as we hear about things like fracking, which is cracking underground reservoirs of natural gas, a component of natural gas is methane.
Right.
And the Arctic is melting, and maybe even Antarctic is melting, revealing pools of methane, which has
an even greater capability of raising the background temperature than CO2 does.
Yep.
So
Yeah.
we're in for double.
Right. Yeah, we were talking about this over dinner. So I showed you a plot of climate forcings. Methane is one of those forcings. And one of the big questions right now with respect to natural gas and fracking is how much methane is leaked out into the atmosphere. And so a lot of people are working really hard to quantify the leakage rate, because at 2%, maybe natural gas is a good replacement for coal. But at 6% methane leakage, and methane is an incredibly potent greenhouse gas, suddenly natural gas isn't looking as good. Right now it looks like it's closer to the 2% end of the spectrum, but with all of these choices comes certain risks. And methane, I didn't hit on it enough in my talk, but huge. It's a huge concern. Yeah, there's more than just one greenhouse gas out there.
Thanks for being here today and bringing your data and your science for us. We all appreciate it. In the last week or so, we saw a story. We talked earlier about perception of the issue itself. In the last week or so, we saw a story relating to an organization here in Chicago, Heartland Institute, and information being taken by Professor Blank, who's admitted that it was unethical to take the information. So now we have two sides of the issue, and an unethical breach of data, and most of us here are lay people. How do we know how to get through that process and know what to listen to and not listen to?
Yeah, it's really, this speaks directly to what I was saying before, which is trust in scientists is so important. And when we see issues where our trust is compromised in someone, it has tremendous impacts. I think that basically the response from the scientific community was that what Peter Glick did was incredibly wrong, was totally inappropriate, and that at the end of the day, that action does not change the overall body of evidence. And that's one of the great things about science, is that it's like, sedimentary rocks that accrete over time. Like the body of evidence has built up tremendously. And what happens in the media, focused on the controversy, these kinds of things, which when you compare it to the overall body of evidence, doesn't change anything, but it still can totally affect our perception, because trust is so critical. And I think, that is why, for me, it's so important to start with the science and be very careful about the advocacy role. And for scientists, it's I kind of think of us like, firemen, but we work on these longer time scales and the risks are harder to see. But it's really, really important that we don't betray trust. And I think that, unfortunately, that was an action that for those who followed it was questionable and affected it. So I think the only thing we can do is just go back to the science. Human frailty, right? We've all made mistakes, and turn back to the data in those moments.
In effect, at least in the story as I read it, what he was trying to release was information saying they were trying to influence opinion, and we don't know, I don't know whether that's factual or not, but they were basically saying, how do we form opinion to decide opinion?
Yeah, there's a very powerful persuasion game that sort of is playing out, and that's why I do think it's really important to come back to the data, because one thing, I showed you this book on public perception, and I've mentioned Kahneman's book. One of the things that comes out in studies of persuasion and how we come to understand issues and how our mind gets changed on issues is that when you're thinking, it's much harder to change your mind, or much easier. That a lot of the persuasive techniques that we're basically surrounded by, advertising for Coca-Cola, you name it, that's kind of trying to get us while we're not thinking, and getting that sort of the amygdala part of our brain, the kind of really super quick decisions that we don't even know why we made them, but we just did, and oops. But when you have a thoughtful audience, a lot of this persuasion research shows that you can't play the kinds of games that have been shown over time. Like the Kahneman book lays it out really amazingly, where if you ask a question but you insert a number and then ask a question that asks you, to say what percentage of something, that number, it's called focusing, that number will trigger your answer, but only if you aren't informed and if you're not being thoughtful. And so I think, sorry if this is like a long-winded way of just saying that being thoughtful, kind of going back to the Thomas Jefferson quote, seeking out information is really, it's the only way that it works, because if you're just kind of working on your gut, these kinds of campaigns can be really effective. Daniel Kahneman should totally thank me, because his book is great, I have to say.
Hi, I really enjoyed your talk so far.
Thank you.
It occurred to me that if you're looking for advocates, one of the places that hasn't been mined appropriately, and I'll preface this with the idea that a lot of U.S. citizens are very religious. In fact, the first lecture that was given here proved that we are a very religious country. So one of the areas that hasn't been mined properly by those who believe that science and religion are not diametrically opposed is the religious intelligentsia, the religious higher thinking. Let's see, can I hold this? It's very hard for me to talk. It occurs to me that we're allowing the people who do not believe in this to formulate the argument. And if we were to look beyond the box of science to, as you said, the emotional side, the more intuitive side of our brains, we might want to look at our religious leaders and co-opt them into this movement, because frankly it is biblical.
Mm-hmm.
And again, a lot of us are people who believe in the book, whatever book it is. So has anybody used that as a forum for addressing this?
Yeah.
Why isn't it coming out more?
Yeah, well, I think that there is a lot of work being done in the religious communities. There's certain groups like Interfaith Power and Light. The Reverend Sally Bingham is doing terrific work, and I think that it's true. I think that this is a message that does have a place in different forums, and that being one. And there are folks out there who are doing it. Catherine Hayhoe is a climate scientist who's actually just written a book with her husband, who is an evangelical preacher, and they wrote a book together to talk about some of the faith-based issues. So it's picking up some steam. Do we need to wrap up? Yeah? One more question?
Will you please speak a bit to the effect agriculture has had on climate change, and then on top of that, the effect climate change is going to have on agriculture?
Yeah, super interesting question. And, basically percentage deforestation, agriculture, a significant percentage, 30% of the global warming signal. And Chris Field, a professor at Stanford, has been doing some really interesting research just on crop yields under different temperature scenarios. And what he basically sees is that different crops have different thresholds. I believe like the yield threshold for corn, I believe, is like 84 degrees. And so again, if you start playing with these statistics, the number of days you go above 84 during the planting season, there's a measurable reduction in yield. And so you can begin to look out over time how this is going to affect crop yields. It's incredibly tricky. If climate models are hard, then coupling them to agricultural yield models is really hard. But there's some basic physics of just yield related to temperature that folks are studying and seeing that tremendous impact and modeling, in some parts of the world, really significant reductions in rice, in wheat. And this is why climate change is viewed by climate scientists as a massive threat, because of the potential to radically disrupt water resources and agricultural yield, right? That's why societies collapse, right? They can't feed themselves anymore. Thank you. That was a really good question. Thank you.
Thank you, Ms. Cullen, for taking the time to come to Elmhurst College for such an insightful presentation. I would like to present you with a gift on behalf of Elmhurst College. I would like to thank you all for joining us this evening and encourage you to attend other upcoming events on campus. Lectures during the next month include Quest lectures. The Shade Lecture on Tuesday, March 6th in Founders Lounge, featuring Martin Marty. He will present H. Richard Niebuhr, A Centennial Appreciation. And Luke Menand will present The Marketplace of Ideas, Reform and Resistance in the American University on Thursday, March 15th at 7 p.m. in the chapel. And Katie McFarland on April 15th at 7 p.m. in Founders Lounge on the topic of democracy and global security. For additional information on these and other upcoming campus events, please visit our website at www.elmhurst.edu. Again, thank you for joining us tonight. Our lectures are free, but they are not without cost. So if you've enjoyed tonight's lecture, please consider making a tax-deductible contribution to the Friends of the Arts at Elmhurst College. You can use the envelope in your program or just hand your contribution to one of the students in the lobby. We greatly appreciate your support. Have a safe trip home.